Yeah, they would like take a picture of like the end screen or something like that. Oops. Okay. Well, there's three of us. Few people are online, it looks like, so maybe they'll join in at some point. So I thought what we do is do a Unit 7 FRQ. So Unit 7 is on the logistic equation. So let me pull up the logistic equation unit guide, and we can take a look at some of the topics on there. So where is it? AP package, gray units. Unit 7, okay. Or I guess Unit 7 is on differential equations, but the logistic equation is like the big kahuna for this. So Unit 7, so let's talk about Unit 7 real quick. I'll try to make this go by fairly quickly. There's, I think, 9 different sections. So this is Unit 7, which is on differential equations. Differential equations. Okay, awesome. So the first one is just modeling differential equations. So that's modeling DEs. By the way, did you know that the Canadian way of spelling modeling has 2 L's? Americans spell it with 1 L. I don't know, but there is. I know. Yeah, at Waterloo I had a professor who was American, and he was one of those Americans who made a big point of being American and how weird it is to live in Canada and stuff like that, and everything is so novel. And then he would make a big fuss about spelling it with 2 L's. Okay, the next one is verifying solutions to differential equations. Okay, so like you're given a differential equation, can you solve for the actual function? And once you have that function, does that function actually work in the differential equation? Differential equation is where you're told, like you're given, you're like an equation is being described by its derivative. So you might have something like y prime is equal to 1/3 of y minus 6, or something like that, times y. So you're told about the function in terms of its derivative, and the function itself appears in the derivative. Okay, so something like what was the was it y prime is equal to y, right? That's the most straightforward differential equation, and when you solve for it, you would get that y is equal to e to the x, right? And then you have to keep in mind, like, this y is a function of x, right? So y prime of x, y prime is a function of x is equal to y of x. The only function where that's true is e to the x, or times a constant, exactly. So yeah, that's what a differential equation is. And keep in mind that when you verify solutions, you have to keep in mind that there is that constant. So sometimes you actually can solve for that constant. I think we did a few examples like that when we were first learning this stuff. Okay, next up, number 3 is slope fields. Everyone's favorite part about DEs, slope fields. Unit 4 is like reasoning using slope fields. So I'll write applying slope fields. Okay, number 5 is Euler's method. I remember a lot of pain went into Euler's method when we were first learning it. Okay, number 6 is finding general solutions using separation of variables. So I'll just write separation of variables. Okay, so that was a topic where you're given some kind of differential equation, and then in order to solve for it, you need to separate the variables. So you can either take a derivative or an integral or what have you, so that all the variables that you want are just on one side of the equation. Okay, number 7. We're almost done here. Number 7 is finding particular solutions using initial conditions and separation of variables. So I guess what I'll say is solving DEs with initial conditions. Okay, so kind of like what I was saying before, where you would actually solve for the constant inside the differential equation. Number 8 is exponential models. Exponential models. And number 9 is my favorite one, the logistic equation. I think so. I'm going to be honest, I didn't learn about the logistic equation when I was in university. In fact, I didn't learn any of this stuff in university. I think I mentioned that I'd never taken differential equations. So I was kind of learning this alongside you, and I think the logistic equation is pretty neat. It's super like complicated, but it's one of those things that it's kind of fun, right? There's a bit of a challenge. This is what I want to focus on today anyways, is the logistic equation. I think it's probably one of the ones that we struggled with the most. I know certainly when I was learning it, this one was the one that I found hardest to learn. So that's what I want to focus on. I also want to focus on it because that's what the free response question that I chose for us to do is centered on. So that's what we'll look at today. Let me just pull up the question. Okay, and I thought, okay, I wonder if, okay, what I'll do is can I copy and paste this? No, I can't. Okay, I'll take a screenshot. Yeah, I'll do a screenshot, and I was able to download as a PDF. So it looks a little bit different than it might look on, how do I do this? Copy. Yeah, it'll look a little bit different than it does on the website, but that's fine. Okay, so I'll paste it in here. I do want to like bring it up in here. I wonder if I can open Discord here, and then there we go. AP Calc. Okay, I'll just copy this or save image, I guess. There we go. Isn't Discord handy? Okay, a picture, this picture, here it is. Okay, great. Oh, it's a little pixelated, but that's okay. Okay. Gray bars on the side. Where are the gray bars? You're on your own, buddy. Like, are you talking about the video or are you talking about the picture? Okay, yeah. Maybe try closing it and opening it again. I don't know. Yeah, I don't think I can change that. That's because just of the aspect ratio. Yeah, because I don't have a 1080p screen. It's like 1920 by 1200, so it's not like the 16 by 9. It's 16 by 10. So anyway, okay, yeah, let's take a look at this question. Okay, so we've got some kind of situation here with liquid fertilizer. Like, they love to sort of talk about a situation, right? But then really the heart of it is the differential equation right here, right? So yeah, they've got this liquid fertilizer, and it gets injected into the growing system as a function of time. The function that they're talking about is the function f. And it satisfies this logistic differential equation. df by dt, I'll write it again here, is 1/3 times f. So let's just remember a couple of things here before we move on. If this was the differential equation, that it modeled, this would be a exponential function. Okay, it would be an exponential function because the function itself is proportional to its derivative. So remember that your derivative is the rate of change. So if your function is proportional to its rate of change, that means that as your function gets bigger, your derivative gets bigger as well, right? So the bigger your function, the bigger your derivative. So you're increasing at a rate that is increasing. The rate itself is increasing proportionally to the function itself. But it is not that. It is it is a logistic equation. So it's not an exponential equation, it's a logistic equation. And the logistic equation says, okay, well, you know what? As you get closer to f, as the function, like the output of the function, gets closer to 6, so as we start to approach 6, this function is going to start decreasing, or the rate, the function doesn't decrease, pardon me, the rate at the function, the rate at which the function increases decreases. So it starts to sort of peter off. So remember that the logistic equation is going to look something like this when you graph it, right? So in this case, as we get closer to 6, the derivative gets smaller, right? So as f approaches 6, right? As f approaches 6, df by dt approaches 0, right? And this happens across time, right? So the further we get, the further as time progresses, we get closer and closer to 6, but then the derivative gets closer and closer to 0, right? So that's how the differential equation works, is that you on the one hand, like kind of around here, it sort of looks like you have this exponential growth, right? The rate at which the function is increasing, like its rate is increasing proportionally to the function itself. But then you get this kind of inflection point right around, oopsies, that's not what I meant to do. You get an inflection point right over here where we're still increasing, but the rate at which we're increasing starts to decrease. So what that means is that our derivative is getting closer and closer to 0 as we progress over here, right? So that's the differential equation. They're also told us that at time t equals 0, so let's say that this is t equals 0, 3 liters of liquid fertilizer are injected into the growing system. So it's right here. So f of 3 is, f of 0 is equal to 3. Okay. And then they tell us, oh yeah, by the way, hydroponics is the process of growing plants in sand, blah, 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 blah. So not really relevant to the mathematics, but still kind of neat. So yeah, this is kind of the situation that we're in. This is the graph that we can kind of work with. And the function, or the first question is saying, find the limit as t approaches infinity of f of t. And if you didn't really know anything about the logistic equation, you'll struggle with this, right? Because it doesn't really seem obvious what the limit is. We're not told a whole lot about what f is. And we have seen that you can solve for f. You get this weird, like, upside down exponential function, and it looks really messy, right? I'm not sure if you remember that, but there was one of the equations that I did ask you to memorize. So yeah, if you didn't know anything about the logistic equation, you'd probably have a very difficult time calculating the limit as t approaches infinity of f of t. But just by looking at the graph and sort of interpreting the situation, we can see that, well, the whole point of this part of the equation here is to say that like f is approaching 6, right? That's the whole point of this, is that as f approaches 6, then that derivative starts to sort of peter off and kind of become more horizontal, and the rate approaches 0. The rate of increase approaches 0. So the answer is just 6. Like you don't have to show any algebra. So for the first one, the limit as t approaches infinity of f of t, it's just equal to 6. That's all there is to it. I went through. Pardon me. Okay, what are you punching 5.5 into? Yeah, remember, this is the logistic equation. This is a differential equation, right? This is a differential equation. That is telling you what's happening to the derivative, right? So this is saying, like, if f of t is 5.5, right, then you'd be able to find df by dt by saying that it would be equal to 1/3 times 5.5 times 6 minus 5.5, right? And you could solve for that. It would be like 5.5 times a half times a third, so whatever that is, 5.5 over 6. So you can even see that as f is approaching 6, the derivative is, well, I guess in this case it's a little bit less than 1. It's like 0. Pardon me? Yeah. Exactly. So yeah. So this right here, as we get closer and closer to 6, so 5.5 is very close to 6. This gets close to 0, and the closer and closer we get to 6, the closer and closer this gets to 0, right? So eventually we're getting so close to 0 that the derivative is effectively 0. So yeah, great. So yeah, this limit is 6, and then because it's a logistic equation, this is true for pretty much all logistic equations, the limit as t approaches infinity of df by dt, it's just 0. The derivative of any logistic equation approaches 0 as time increases. So that's really all there is to that one. So I think it's a good question because it doesn't actually require any real algebra or calculus or anything like that. You just have to have some understanding of what the logistic equation is, how it works, and that kind of thing. So let's see here. Let's do part B, if I can find it. Where did it go? Give me 1 second here, sorry. Oh, here it is. Okay, part B. Now, part B, we covered this little tidbit, and I'm really glad that we're doing this one now, because chances are you have forgotten a few important facts about the logistic equation. So I'm gonna paste this one in to the chat again, and then I'll put it back on my iPad. There we go. So basically the question is asking, at which point is the derivative increasing the most? Okay, at what point do we have sorry, what is it asking again? Yeah, basically, where's the inflection point? Yeah, so find the value of df by dt at the time when f is increasing most rapidly. So give a reason for your answer and indicate units of measure. So let's take a look at that one. Okay. So B, oh yeah, and let me pull this up again. How did I do that? There we go. Copy. Where's copy? Save image, there we go, that'll do. throw that in here. Okay, find the value of df by dt at the time when f is increasing most rapidly. So we want to know like the maximum rate of change in this. Okay, so just a couple of things. Let's draw this differential equation again. So, oops, should make that a little bit lower. So here's my x-axis, here's my y-axis. Actually, I should make this y and this one t, right? Because it's time that's increasing. And we have this sort of this maximum value here, right? This is the value that the function is. I guess I'll put this by the axis over here. This is the maximum value that our function is approaching, right? So we have something that looks like this. Okay. And they're saying, oh, and also this is 6, right? Or sorry, 3 rather. 3. So I guess actually this is not the best drawing. I guess what I can do is I'll just change the axis. That'll make it a little bit easier. Yeah. Okay, so if that's 6, that's 3, then about here-ish. Let's say that this line is the time axis. Okay, so and also let me, you know, sorry, I just have to change this a little bit, otherwise it's going to bug me. So it's going to look something like this, right? So here's the thing about a logistic equation is that we've got sort of like two things going on here. We have the maximum value here, and we have a minimum value here. Now, in pretty much all of these situations, we are going to have that the minimum value is 0, right? Because usually what we're talking about is some value that could be equal to 0, like population, right? It technically could be 0. Am I still online? My thing just glitched. Am I still online? No? Okay. Yeah, I just saw a gray screen. Okay, here I am. Am I back? Looks like I'm back now. Okay, sorry about that. Yeah, so what I was saying is that you have a maximum and you have a minimum. So usually the logistic equation is talking about some value that could be equal to 0, but pretty much never is, like population, or the number of people infected by a disease or something like that. And there's a minimum and a maximum. And what happens is as our function is close to the minimum, there's not really a whole lot going on, right? So like for population, the population doesn't increase very much while the population is low. So you get this sort of this slow creep when the function is close to 0, right? As you get further away, kind of like an exponential function, as you get like more of a population, the rate at which you increases itself, right? So you get this sort of increase, sort of exponential looking thing. But then at some point you kind of start to hit this limit, and then you start to decrease. And that point, that key point, is right smack dab in the middle, when you're halfway between your maximum and your minimum. So that's really all there is to it. So when is df by dt increasing the most rapidly? So df by dt is increasing most rapidly, or I guess I should say f is increasing most rapidly, or in other words, df by dt is at its maximum. So f is increasing most rapidly when f of t is equal to 3. Okay, so that's the maximum value of f. So really all we have to do is figure, okay, well, what's df by dt when f is equal to 3? Because the maximum is 6, the minimum is 0, and then the middle value, which happens to be right here when time is equal to 0, but that's not what they're asking. But yeah, you can the way like the best way to solve these isn't to sort of try to solve for f and then find like a maximum or something. The best thing to do is just to take a look at what the logistic equation physically looks like and say, okay, well, at the maximum value here and the minimum value here, like around the maximum value, the derivative is close to 0. Around the minimum value, the derivative is close to 0 as well. But then in the right smack dab in the middle, that's where it increases the most. So since 6 divided by 2 is equal to 3, that's where the 3 comes from. So if we want to find what df by dt is equal to when f equals 3, well, we just plug it into the differential equation. So that's equal to 1/3 times, well, f is in this case equal to 3, and I've got 6 minus 3, and that would be 1/3 times, oh, I guess these would, these would cancel out, and I would get 3. So that's, so the rate in which it increases is 3. Now it did ask for units. Let's figure out what the units are. So we have to go back to the original question. So it would be liters of liquid fertilizer, and time is measured in months. So that would be 3 liters of fertilizer, liters of fert per month. Yeah, that looks bad. Fertilizer. Okay. Yeah, so that's pretty much it. Now, if you wanted to, like, if you don't understand this whole like maximum, minimum, middle business, you could solve for it. I mean, we could use a little bit of algebra. Do you want me to do some algebra for that? Yeah. Did not ask when. No. The question says find the value of df dt. Yeah, when f is increasing most rapidly. Okay, cool. So let's just take a look at what this df by dt looks like. So what we're going to do is we'll say, okay, well, what is it? 1/3 times f times 6 minus f. Well, let's expand this. So this is going to be 1/3 times 6f minus f squared. Or in other words, that's 1/3. Well, actually, you know, we don't even, like, it's already factored. What am I talking about? This is a quadratic equation, right? It's a quadratic equation because if you expand it, you'll get like 1/3 of f squared, or negative 1/3 f squared plus 2f, right? That's what the equation actually is. So if you factor it, what you can do is you can say, okay, well, this is a quadratic equation. The stretch factor, I mean, it may have been a while since you guys have done quadratic equations, but the stretch factor is negative 1/3, so it's pointing downwards. And its roots, the roots of this equation, are when these are equal to 0. So when either f is equal to 0 or f is equal to 6. So f equals 0, f equals 0. And then so the maximum, so that like this graph that I've drawn here, this axis is the f axis, and then this y-axis, this up and down axis, is the df by dt axis. So basically what I'm doing is I'm looking at the relationship between df and dt. So if you were to graph this, then you would get this quadratic equation. The maximum, it doesn't even matter what the maximum is, it's going to be in the middle of this quadratic equation. So when this is equal to 0, that's one root. This is the other root, right? The vertex of a quadratic equation, so I should say the vertex of a parabola, lies right smack dab in the middle between its two roots, if it does have roots. So the vertex is going to lie right in the middle between these two roots here. So that's another way of thinking about it, that, well, obviously, one of the roots is going to be when f is equal to 0. The other root is going to be when f is equal to 6. So the maximum value is going to be between 0 and 6, which is, of course, 3. So that's another way of solving it. But just by eyeballing it, you can kind of just take a look at the graph. So I highly recommend that you graph these things and say, okay, well, right smack dab in the middle, that's that one right there. So that's right between 0 and 6, which is 3. Okay. Any questions so far? Am I going too fast, or are we good? No? Okay. So let's do, what is it, part C. And there is a part D as well, but I think I'd like you just to do part C, and that'll be your exit slip for today. So it's not too bad. Where is part D? Oh, actually, no, I don't want you to do part D. Yeah, just part C. And I'll just write what part C is. I won't bother copying and pasting it into the chat. This one's super easy to write down. So part C is the following. So find d2 by dt squared. So the second order derivative of f, okay? In terms of f. Good question. In terms of f. Yeah. So yeah, basically all we're asked to do, so I know that this is, so df by dt is equal to, what was it? 1/3 times f times 6 minus f. And now we're asked to find the derivative of this. So basically d by dt of this. But we're going to keep it in terms of f. So we don't have to worry too much about converting it into a function of time. We're just looking at it in terms of the function of f. So I'm gonna leave that one with you, and it's not as hard as you think. I mean, maybe you think it's easy, maybe you think it's hard. There's several ways of doing it. You could expand it and treat it like a polynomial. You could use the product rule. There's several ways of solving this. So just keep in mind, I want your answer in terms of f. So don't think that you have to, convert it into, figure out what f is and all that. Just take the derivative of this guy and keep it in terms of f. So I'm going to leave you at that. I haven't taken a look at the assignments yet from the AP Classroom. I just finished marking a different assignment for a different class, so you guys are next on my list. So I'll start marking these. Honestly, probably not today, but I'll start marking them tomorrow. And yeah, let me know if you're having any difficulties. I know that there was a few difficulties on some of the questions last time. I haven't heard anything about the new progress checks, but let me see if anyone's actually doing them. Yeah, it looks like maybe these ones haven't really been started. So I guess this was my fear of unlocking all of them at once, was that people might feel a little overwhelmed and not be super motivated to do them. But looks like a couple people have handed them in, so that's good. But yeah, remember that I assigned progress check 6 yesterday, and I'm assigning 7 today. 7 is already open, so now we're actually kind of looping back to the territory where I was assigning this as we went. So when we first did the differential equations, I assigned this. So yeah, now's your time to do it. I don't think anyone did any of these when I first assigned them, so that's why it's still okay to enter them now. Anyways, I'm just rambling at this point, so I'm gonna sign out. Yeah, what's up? Oh, no, we didn't. I'll get those to you by this weekend. Yeah, I'll give you those tests by the weekend. But yeah, I never quite finished marking those. But yeah, good question. I'll get you those this weekend. So I'm gonna sign out now, and I'll talk to you guys tomorrow. If you have Any other questions about this material, don't hesitate to reach out. And good luck with this exit slip. So this, by the way, if that wasn't clear, this is your exit slip for today. And yeah, I'll talk to you guys tomorrow. Okay, bye-bye.